Alright, so I was looking at sort of the Hayes 2001 logic of optimizing a number system, finding an optimum number base for uh, a numeral system. And if so, one of the assumptions that Hayes is making is that the number of symbols in your system is the same as your radix. Okay, so taking Hayes' 2001 approach of approximating the number of digits in a string representing integer n and base b of ln of n on ln of b, and estimating the efficiency as this multiplied by the number of symbols b and abstracting away the n component, we arrive at b on ln b. Okay, so this is a rough approximation. So for like ridiculously large values, it should become more and more accurate. It should be an asymptotic, roughly, behavior. So that's kind of important. So like for small numbers, they're going to do what they're going to do. Now, it's notable that the number of symbols does not in fact have to be identical to the radix, right? And the number of symbols can, and in practical systems virtually always does, differ from the radix, which very poorly devised systems like Roman numerals requires an unbounded number of symbols to represent all possible integers. And very well-devised systems like Mayan numerals require far fewer symbols than the radix. Thus, our approximation for efficiency of b on ln b should really be adjusted to decouple the number of symbols, s, in the numerator from the radix r in the denominator, yielding an approximation of efficiency s on ln r. This is really the same exact approximation. We've just reflected the reality of practical and attested number systems, that the number of symbols and the radix do not have to be exactly the same number. There's no reason for the number of symbols to be identical to the radix. Okay, so having b in both the numerator and the denominator is kind of a silly assumption, right? Because there's actually pretty much, in the real world, there's virtually no number systems that have been devised by humans which operate this way, apart from the one that we use in the modern world. But the fact that that came to be dominant doesn't actually mean anything other than it's the one that came to be dominant. That's pretty much just a random-ass quirk of history. So now the dynamic becomes different, since b on ln b has a minimum on the right branch at e. So if you look at if you graph it out, there's two branches for values. What is it? I don't have the graph in my head. But there's a left-hand branch that goes from 0 to like 1, I think. And it's negative. It's below the x-axis. And then the other one, it goes down to negative infinity. And the other one, from 1 into the infinitive, or positive infinity, it starts off at positive infinity, crashes down to e, and then it goes off pretty much linearly at a shallow angle to positive infinity. So you get a minimum on that right branch at e. But s on ln of r has a right branch that asymptotically approaches 0 for positive s and r as r grows larger than s. So depending on what you choose for these values, if your r value is arbitrarily larger than s, then we're approaching 0. Whereas their best one for b on ln b was approaching e, we can approach 0 here. And the whole goal is to minimize it, right? We're looking for that minimum, so we want the smallest possible value. So by decoupling the number of symbols from the radix, we can actually achieve efficiencies in a number system that are vastly superior to base E, the Hayes alleged maximally efficient number base. Thus, for my number system of 60, 60, 77, 52, the radix r is 14,414,400. That is 60 times 60 times 77 times 52. But the number of symbols, which represent digits, there's some other ones that clean it up and make it easier to read, but the ones that represent digits, s, is only 7. Right, so we can represent 0, 1, 2, 3, 4, 5, and 6. Resulting in our estimation of efficiency being s, or well, that should be 7. Might as well just be 7. I don't know why I put s up there. 7 on ln of 14,414,400. ln of that number is a little bigger than 16, so we get a little bit less than a half. Right, so it's approximately 0.4246, 4247. Since the point here is to minimize this value, and our value here is about 1/7 the value of e, which was the minimum for a number system which coupled symbol count and radix, it is fair to say that my number system is significantly more efficient than the most efficient choice of radix which Hayes considered. And this is using Hayes' own logic. Using Hayes' own logic, my number system is massively more efficient than the most efficient one he could find. For comparison, the Mayan number system results in efficiency value almost identical to 1, right? And this is because there's 3 symbols, one for 0, one for 1, and one for 5, and the radix is 20, which is extremely close to the value of e cubed. So we basically just get 3 divided by 3, right? So the ln of 20 is really, really close to 3. It's like 2.99 something. So we're just dividing 3 by 3, more or less, and we get 1, more or less. Like, it's super close. It's like within like 1/7 of a percent. Like, it's stupidly close to 1. It's basically just 1. So this is roughly e times better than base e. So you have an existing number system, which was available to Hayes for analysis, that is e times better than his claim to the most efficient number system, which was base e. That's kind of amazing. This is the way science usually works. Like the people that come up with these things, they're just unaware of stuff. So it's not that, given his considerations, I don't think he's wrong. I think his approximations, given what he's doing, I actually think that his logic is sound. The thing is, in a real number system, the number of symbols and the radix are not actually coupled. That's an artificial simplification which came about. I'm not sure when it was really introduced, but it was definitely promoted pretty heavily in new math when that was taught post Sputnik in the U.S. It's mostly in the 60s. Because as a promotion of basically very similar to current day STEM. Basically, there was this fear that the Soviets were massively superior in their knowledge of mathematics and that sort of thing, engineering and computer science and shit like that. The new math that was introduced post Sputnik, post 1957. Involved a lot of treatment of number bases, but it included this simplification that the number of symbols is identical to the radix. That is an integral component of the way that it was taught. So there is this generation that's just how they see it. That's just how they think it operates. But when you actually look at real number systems, it doesn't operate that way. The number of symbols is not coupled to the radix necessarily, and you have really shitty number systems like the Roman numeral system, which is just fucking trash, where you basically need an infinite number of symbols to represent arbitrarily large numbers. And then there's really beautiful systems like the Mayan numeral system, where you only have 3 symbols. You can represent anything with those three symbols, and it's not fucking ternary. It's base 20. Like, that's beautiful. That is beautiful. Okay. So now it should be fairly obvious that my 60, 60, 77, 52 system should probably be somewhat more efficient than Mayan numerals, since it directly expands on the Mayan number system. So what I did when I was setting that up, the 60, 60, 77, 52, one of the things I was looking for was I'm trying to incorporate prime numbers. One of the things I was looking for is I'm trying to use powers of 60 or very close approximations of powers of 60, because we use that a lot in our daily lives, actually. So like the number of seconds in an hour is 60 times 60. So that's a power of 60. Being able to express that nicely would be lovely. And 60 can just be represented as 320s. And so having a number system available to us, like the Mayan numeral system, which is already base 20, and just building from that, that made sense. So I really did that. I really did devise the whole system as in sort of an expansion or an interpretation of the Mayan numeral system. So if the Mayan numeral system is super efficient, and the things that I'm doing are only aimed at making it even more efficient, then it shouldn't be any surprise that that is the result. And also, in fact, my system rendered in a non-cursive style. So the cursive style is actually analogous to the historical development of the Western Arabic notation, where our symbol for 3 is just a cursive style of writing 3 dots, where you don't pick up the pen, right? So you get these ligatures between the dots, and that's where the curves for the 3 come from. The 2 is basically the same thing. We've got these two like strokes. So there's the top stroke and the bottom stroke, and then you get this ligature between them, which makes it look more or less like a Z, right? And then the 4 is like an X, but it's got a ligature at the top, which links that together. So you get the 4 shape, right? And then 5 is, it's basically a 1 and a 0, but the 0 is written fast, so it's open, and you get a ligature between the 1 and the 0. So you get, and it's written so the 1 is above the 0 horizontally, so you get our symbol for 5. Like, that, some of that history I actually built into the cursive style, so that some of the number forms would be sort of familiar, right? So like my version of 2 is basically like that, right? 1 is just a dot, 2, 3, 4 I usually represent as a G, the idea being that like a gamma, a lowercase Greek gamma, looks pretty much like a cursive X, you know, that sort of thing. But if we take it out of the cursive style, the idea is that a 4 is really 4 dots, and they're just arranged in a special way. They're arranged in a square. And when you write that in cursive, it becomes sort of like an X. And then when you write that really fast in cursive, you get a ligature between, when you write the 2 strokes, you get a ligature there that links them, and it basically gives you a shape like a number 4. But the orientation of it in my writing is different than it is anyway. So if we take it out of the non-cursive style, the number of symbols more closely approximates the Mayan system. Now we get a 0, a 1, a 5, but also a 6 because of some of the modifications I had to make to it. So we've got 4 symbols, 4 digits, and we're still going to be dividing that by the ln of 14,414,400, which is a little over 16. So that gives us just under a quarter, right, of our approximation for efficiency, right? So this is the idea. The goal is to minimize this value, right? The smaller this value is, the more efficient the number system is. So this is the smallest value that we've seen, And this value is over 11 times the efficiency of a symbol radix coupled base E system. 11 times. That's insane. And this estimation of efficiency is not even taking into account usage efficiency, where things like being divisible by a large number of factors is very nice. And my number system is, because it's built around an antiprime, right? It's divisible by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, not 17, 18, not 19, 20, 21, 22, not 23, right? A shit ton of numbers. It's divisible directly by a shit ton of numbers. So that alone makes it even more efficient, right? Because an approximation to base E, you're going to be using 3 or 2. That's not divisible by 5. That's not divisible by 7. That's not divisible by 11, right? You run into problems almost immediately. Right? Very small numbers don't divide into this, and that makes it comparable in that regard to a base 10 system, which just has... It's almost prime. 10 is almost prime. It's so shitty. It has so few factors that it's almost prime. We might as well just use base 11. It wouldn't be that much worse. Whereas here I'm using an anti-prime, and a very large anti-prime, so with a very small number of symbols. So it is, in real senses, very, 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 very much more efficient than any fucking number system that I've ever seen outlined by anybody else, ever.